Hello, welcome everyone. I'm Thejas Chakrapani, a postdoctoral scholar at Technical University of Delft in the Netherlands. And I've come up with these video lectures on the hydrogen thermodynamics toolbox, specifically designed for underground hydrogen storage. And the main goal of this toolbox is to collect data that is useful for underground hydrogen storage. So this could be anything related to the densities of pure hydrogen or hydrogen mixtures, and it could also be related to the various other properties of hydrogen mixtures that are useful uh, to build or to feed data into reservoir simulators and so on. So that's the main idea of this hydrogen toolbox. So what I wish to cover in these videos is that firstly, I want to show you how a particular database looks like. So this is an Excel file where I've collected all the data that has been uh, collected from molecular simulations from the from our group. Now, to show you one specific example, I will look at this particular sheet called the mixture properties hydrogen carbon dioxide. And in this sheet, what you can see is that the densities of hydrogen carbon dioxide mixtures that you see in column E has been tabulated for for many different thermodynamic state points. And these thermodynamic state points are basically the pressure, temperature, and the hydrogen mole fractions. So these are basically densities for hydrogen carbon dioxide mixtures at a given pressure, temperature, and hydrogen mole fraction. So you have around 550 data points here, as you can see. Yes, so 550 data points. And what I wish to do with these videos is to instruct you or show you how you can add more data to these sheets. So this is just one example where I've looked at the mixture property of hydrogen carbon dioxide. After viewing these lectures, after going through these lectures, you must be able to add, or you can add another data point if required, or a set of data points. So for example, you can probably perform a new simulation, or you can collect data from a new simulation at, say, 55 megapascals and around 300 Kelvin, and then for a equimolar mixture of hydrogen and carbon dioxide. And then you might be able to fill in all of these columns here. So that is the basic purpose of these video lectures. Now, what I wish to do is, yes, another thing that I wish to mention is that these properties have been mainly collected, or they have been computed from molecular simulations. So molecular simulations have become quite popular for scientists to measure or compute data reliably, because they compare excellently with experiments, because the force fields have become quite accurate, and they've become a very versatile tool for collecting data, for computing data, which is useful for many applications. So I'm a computational scientist by background. So I'm going to be discussing how to compute thermodynamic properties using molecular simulations. Okay, so given that I'm here to tell you how to expand this hydrogen data set, I should also be able to tell you how to perform a molecular simulation, right? So that's the basic idea. To perform a molecular simulation, it's also good to sometimes go through the basics of molecular dynamics simulations, which is the key goal of this first set of lectures. I wish to cover the basics which are relevant for the simulations that I'm going to talk about, or the simulations that were relevant for the collection of the data sets. So at the end of this lecture, what I want to do is to show you one hands-on example of how to calculate the density of hydrogen at, say, 5 megapascals and at 5 megapascals and 323.15 Kelvin. And you see here that its density is roughly around 3.7 kilograms per meter cube. So we will try to see how we can calculate this particular data point using molecular simulations. So that's the goal of my lecture. So the basics of the molecular simulations will then be to help you get to this final data point, or to compute this particular data point. And we'll be doing all of this using LAMMPS. So that's a well-known software that's used in the molecular simulations community for large-scale simulations of, it could be molecules, for materials, basically, or it could be for granular materials, or it could be for fluids. So it's a very well-known software that people have been using for quite some time now to calculate thermodynamic properties or even dynamic systems. So in these lectures, I will also tell you how to set up LAMPS. And then finally, as I said, we'll compute the density of hydrogen at 5 megapascal and 323.15 Kelvin using one of the LAMPS software. And hopefully this will help you get started into this entire thing. Okay, now let's get into the basics of molecular dynamics. My aim here is to not tell you all the details and all the basics, because these are pretty well documented in many good reference books. And for these lectures, I am mainly taking content from these two textbooks, which is Frenkel and Smith, the third edition, which was released somewhere last year. And then the other book is by Allen and Tildesley, which is the 2017 version, which is the second edition. And these two textbooks are considered to be highly, these are basically the Bibles of this field. Yeah. So these are the main references that I'm going to use for these lectures. And I've also taken many of these contents from Dr. Othonas Moultos. So he's an assistant professor here at TU Delft, who has made very nice video lectures. So my thanks goes out to him for helping me with the content of these lectures. All right. So to put the entire thing into perspective, I will tell you where exactly the molecular simulation or in which domain does the molecular simulations are broadly placed. So on the y-axis, you have the time scale, and on the x-axis, you have the length scale. So when you're looking at molecular simulations, you're mostly in the regime where your time scales or your length scales are between angstroms and slightly greater than a few nanometers. So that's this particular range. And in terms of the length scales, you're more or less in the range of picoseconds to a few hundreds of nanoseconds. So you're not really looking at very big systems. You're looking at a very tiny systems, but the importance of these, even the importance of these tiny systems is that you can collect quite a few useful information just using such small, tiny systems. That's the whole idea of looking at molecular simulations, because here you do not make any assumptions and you start from the bottom-up approach. And at the end, you can make very useful predictions about the thermodynamic properties and about many other transport properties that are relevant for many large-scale systems. The nice part about molecular simulations is that you can also then feed the data that you get to the larger or the bigger scales, which are same, say, in the length scale of kilometers to meters and so on. Okay, so what is a molecular simulation? So you can think of molecular simulation as just another experiment. So how you would do an experiment in a lab, molecular simulations is exactly a similar procedure of doing a computational experiment, but you're doing this on home built, or you're doing these experiments on molecular models, so to say, or particles. The main idea here is to prepare a system, make an initial configuration, allow the system to equilibrate, allow the system to reach its equilibrium state, and then generate many configurations of the system corresponding to the same state. And then you can perform a measurement once you've reached equilibrium. And this measurement can correspond to any property that you're interested in, or it could be related to any other phenomena that you're looking at. Now, these simulations have been, they can be quite complex, right? So it can simulate as simple as gases, monoatomic gases like argon and krypton and so on, to quite complex materials like polymers and even biological systems. So these simulations have grown quite a bit and can simulate quite a few complex materials. Now, what's important to know is that we typically use something like 1,000 or even 10,000 or sometimes even a million atoms to simulate molecular simulations, or to simulate a system, or to represent a system. And this turns out to be quite sufficient, and it can also help you give accurate estimates of the properties that you're looking for. So now let's look at what are the common molecular simulation methods. What I'm going to deal with in these lectures is mainly molecular dynamics. The idea of molecular dynamics, like I told you, you can start out by doing an initial configuration. Once you have an initial configuration, you solve the Newton's equation of motion, and these equations of motion give you deterministic positions and velocities of particles. And then you basically get a trajectory. So Newton's equation of motion is basically F is equal to ma, where F is the force on a particle or a molecule, m is the mass of the molecule, and a is the acceleration. So you're solving these equations for all the molecules inside the box. And then you could create a trajectory of the system, or movie of the system, where each snapshot corresponds to one instant in time. And you just integrate the equations of motion for every time step, and then you create this kind of a movie. And once the system has reached steady state, you can calculate properties such as viscosity, diffusion coefficients. You can also try to understand how the molecules are placed relative to each other, what's the typical distance, what is the inherent structure that the molecule or the system contains, which is characterized by the radial distribution function called the G of R. You can also calculate interfacial tensions, how the molecules are placed at the interface, and so on. So you can predict a whole lot of properties. As you can see, this is how a typical molecular simulation looks. The positions of these atoms are moving smoothly over time, and this is a result of solving the Newton's equation of motion. Now, there's a very useful technique called the Monte Carlo simulation technique. And in Monte Carlo simulation technique, you're not really interested in how the molecules move over time. What you're interested in is to only sample the configurations relevant to your property, or relevant to your system. So the motions are then stochastic, they're not smooth. So you make random changes to the molecule positions, and you see if these random changes or random translations of molecules are acceptable based on based on the energetics of the system. So I will come to this at a later point in time, but right now, all you need to know is that the Monte Carlo simulations are not are only stochastic, and you make random moves, and you are only interested in sampling configurations. So you're not interested in the velocities of the particles and so on. Similar to molecular dynamics, you can also compute lots of important properties like phase equilibrium. So if you're looking at hydrogen and water, for example, then the phase equilibrium tells you how much of hydrogen can dissolve in the water or how much of water can evaporate into the gaseous phase. What you can also calculate is adsorption. So in many of the cases relevant to hydrogen storage, one can think of how to calculate or how to estimate the amount of hydrogen that is adsorbed onto the surface of clay. So in these kind of scenarios, one would typically choose a Monte Carlo simulation. It is not that you cannot do it using molecular dynamics, but you can do this with Monte Carlo with efficiency, and you can also do it in a faster manner. What you can also look at is reactions. In reactions, then you're looking at how hydrogen reacts with, say, carbon dioxide or any of the other reactions which might be useful for a particular technology, you can then do using Monte Carlo simulations. As I said, in Monte Carlo simulations, you are interested only in generating configurations that are relevant to the system. And based on that, you calculate the properties using the configurations that are finally generated. Here is a movie where you see that the positions of the molecules are no longer changing smoothly with time because you are doing random changes to the molecules and you're checking whether these moves are acceptable or not. So if a move is accepted, then you update the system. And if it is not, you keep the system as it is. So as a result of which, the overall evolution, so to say, of the system looks quite stochastic. Now, what is interesting is even though you're doing molecular simulations, either using molecular dynamics or Monte Carlo, the average properties that you calculate from both of these simulation techniques must be identical, which means that there is no difference in the final calculation of the properties, whether you choose to do molecular dynamics or whether you choose to do Monte Carlo. So this is a good check to see if both of your codes give you the same set of properties for a given system. So if you're choosing to calculate the density of hydrogen, like I said, at 5 megapascal and 348.15 Kelvin, it doesn't matter whether you do molecular dynamics or whether you do Monte Carlo, you should end up with the exact same density, given that you run your simulation for a long enough time. All right. So now I told you what are the different types of molecular simulations. Now I would get into a bit more of details of molecular dynamics because the first example that I'm going to show you is for the density of hydrogen deals only with molecular dynamics. Yeah. All right. So now some of the key concepts in molecular dynamics are the total energy. So now the total energy of a particular system is split between the potential energy and the kinetic energy. So let me show that. So you have the potential energy and then you have the kinetic energy, and the total energy, the potential energy, so to say, comes from the positions of the molecules. So here is a box where I've populated these blue spheres, and these blue spheres are all distributed inside the box. Now, if I consider this to be my origin, then the position vector of each of these blue balls is then R1, R2, R3, and so on up till Rn. So now if you want to calculate the potential energy of this entire system, then it basically comes down to the positions of these individual balls. Now, to calculate the kinetic energy, now all of you are very familiar with your classical, if not classical mechanics, high school mechanics, that the kinetic energy is given by half mv square. So this is no different in the case of molecular simulations. You calculate kinetic energies exactly in the same way. So you calculate half mv square for every ball, for every molecule, and then you sum that over all the molecules inside the box. So that gives you the total kinetic energy. And the velocities is a vector. So if you choose a particular ball, you have velocity in the x direction, you have velocity in the y direction, and you have velocity in the z direction. So I would say this is x. Oops. This is y. Sorry for that. And this is z. All right. So these are the velocities. So in a system, if you want to calculate the total energy, this is how you would do it. Now, if you want further details regarding this, you can read section 5.1.2 that's available in Frankel and Smith. Now, also a common thing that you always encounter in molecular simulations is how to calculate the temperature. So the definition of temperature is derived from the kinetic energy. So the way you calculate temperatures is first you evaluate the total kinetic energies. This is easy because you know the velocities of all the particles at any given instant of time. And once you know the velocities of all the particles, you know the kinetic energy. Now, you can also represent the kinetic energy in terms of the momenta, right? So the momenta, as you know from, again, from high school, is that it's P, or it's a vector as well, is a product of the mass and the velocity. So that is a momentum. So then the kinetic energy becomes the square of the momenta over 2mi. Now, there's a very famous theorem called the equipartition theorem, which tells you that you can allocate a half kT, where kb is the Boltzmann constant, and T is the temperature, to every quadratic degree of freedom, quadratic degrees of freedom. So since your system can have nf degrees of freedom, the total kinetic energy can then be written as a half kT, which is the energy per degree of freedom times the total degrees of freedom. So then, as a result, your temperature using this and using the definition for kinetic energy, you can equate the two, and then you end up with the definition of temperature, which tells you that the total temperature is 2 times the kinetic energy. So the 2 goes here, and it's divided by the Boltzmann constant times the degrees of freedom. Now, what's important to know is that the degrees of freedom are, so for a system that I can show in the previous slide. So for this particular system, suppose you have n particles, then the total degrees of freedom are 3n. Oops. So the total degrees of freedom are 3n. And why do I say 3n? That is because each ball or each molecule can either move in x, y, or z. So each molecule can move in X, Y, or Z. And this, you can do it for n particles. And that is why you have 3n degrees of freedom. Now, let us say that I'm doing a simulation where I want to fix the energy of the system. If you want to fix the energies of the system, then what it means is that you have to somehow control, or you have to put a bound on the potential energy of the system. So you're saying that the system should access those positions in which the balance between the potential and kinetic energy is maintained such that the total energy is a constant, which means that there is a restriction on all the positions in some way. So then you remove 1 degree of freedom. Now let us say that you also want to remove, or you also want to simulate the system at a constant momentum. So if you want to simulate the system at constant momentum, then once again you have to fix the x, y, and z velocities of all the. You don't have to fix the x, y, and z velocities, but you have to fix the sum of the x, y, and z velocities at a constant value. So which means that you remove 3 more degrees of freedom. So finally, what you end up with is 3n minus 4 degrees of freedom. So this is the degrees of freedom for this simple box of molecules if you want to have a system with energy conservation and momentum conservation. And if you do not have any conservation of momentum or energy, then your total degrees of freedom is just 3n, which corresponds to the uh, x, y, and z coordinates that each of the molecule can access. So this is precisely what I'm trying to show here, that your degrees of freedom are 3n if you're just looking at a simple box. And if you're looking for a system with a fixed momentum, then your degrees of freedom are 3n minus 3. And then if you're looking for a fixed momentum and energy, then it's 3n minus 4. So this is how temperatures are calculated in molecular simulations. So it's very important that you take into account these degrees of freedom, because if you're looking at systems containing just 50 molecules or 60 molecules, then the importance of the degrees of freedom becomes quite important. For a detailed discussion, like I said, please visit section 5.1.1 of Frenkel and Smith 3rd edition. Okay, so now that we know how energy is defined and how the temperature is defined, let's also look at how pressure is defined, because these are commonly used for many of the calculations. All right, so now pressure is broken down into two parts. One is the ideal part, or one is due to the ideal gas, which is rho kT. And the second one is called the virial contribution, which comes about due to the intermolecular interaction between the molecules. Now, you all know that the ideal gas law is given by this particular expression. PV is equal to NKT. So now this first part just corresponds to those uh, corresponds to the ideal gas law, and the second part corresponds to then the interaction between the molecules that are at a distance Rij. So what it's telling you is that the idea of pressure at the molecular scale comes not just from the velocities, but also due to the positions between the molecules. And here, once again, the D here corresponds to the dimension of the box, and the V is the volume of the simulation box. So this is quite an important definition that you come across for molecular simulations. Now, what is important to note is that if the force if the intermolecular force between the molecules goes to 0, then your your entire term due to the configurations of the molecules drops out, and you just end up with the ideal gas equation uh, for the pressure. All right. Once again, all of these are well discussed in section 5.1.5 in Frankel and Smith, and also in Allen Tildesley. Okay, another important concept in molecular simulations, whenever you do molecular simulations, is to choose the right ensemble, because based on the ensemble that you choose, you can calculate certain properties. Now, for example, okay, let us start with the simple example of isolated system where you have a NVE ensemble, or called the microcanonical ensemble. Now, in a microcanonical ensemble, what happens is that there cannot be any exchange of matter. There is no exchange of work across the borders of the box, or there's no exchange of heat across the simulation box, which basically tells you that the number of particles is constant because the matter is constant. The volume is constant because there is no movement of the boundary. So the volume of the box is constant, and totally the heat, there's no heat that's escaping the system, and eventually your energy is also constant. So these simulations are native to molecular dynamics simulations, which means that if you prepare a simulation box and you just simulate the molecules, then you're looking at an NVE simulations. Now, there are several cases where you would be interested in understanding the properties at a particular temperature. So you know what the volume of the box should be, because you know how many molecules are there at a given in a given volume, and you're interested in how the molecules behave when you fix the temperature. So that's called the canonical ensemble, or the NVT ensemble, where you fix the matter. So there's no movement of matter across the boundaries. You don't do any work across the boundaries, so the volume of the box does not change. But what you can do is to allow heat to be exchanged with the boundary, which means that the simulation box will somehow exchange heat in such a way as to keep the temperature more or less uh, constant, or keep the temperature to a value that you have fixed. So this is the NVT ensemble. And in an NPT ensemble, then what happens is that there's no exchange of matter, but you can now certainly change the boundaries of the box. So you can expand or contract the box. And you can also add heat to the system so as to maintain the temperature. So if I say that I want to simulate hydrogen, or I want to calculate the density of hydrogen at 5 megapascals and 323.15 Kelvin, since I talk about this particular system because we have chosen to work on this system, then you would choose an NPT system to get the densities, because you know the temperature and you know what is the pressure that you want to determine this density at. So then what would happen is that the box would fluctuate, it would increase or decrease and so on, ultimately to give you the right densities, because the density is then the number of the mass of the simulation box given by the volume. So in such a case, you would use NPT simulations. So choosing the correct ensemble becomes very central to performing the right molecular simulations. For example, you will not be able to simulate densities, or you will not be able to compute densities if you're looking at a canonical ensemble or the NVT ensemble, because you do not know what is the volume that a particular mass of hydrogen would occupy if you're at temperature 323.15 Kelvin and a pressure of 5 megapascal. So that is something that you have to find. or that is something that you wish to know as an output. So for a discussion on the ensembles, once again, you can refer to Finkel and Smith because there are various other ensembles that are available depending on what kind of properties you want to look at. All right, so we more or less know some of the basics now. Let's look at a bit on how to perform MD simulations. So the entire procedure can be split into these 4 parts. The first part is to perform an initialization where you fix the initial positions and velocities of the molecules inside a box. So I will always get back to this particular figure. So you can assume that this is a box, a simulation box, where you have defined the boundaries. So you have said what should be the minimum x. So assuming that this is the x-axis, and this is the y-axis, and this is the z-axis. So you have specified what should be the minimal x-axis, the maximal x-axis, minimal y-axis, maximal y-axis, and also the minimal z-axis or the maximum z-axis. So you have defined a box and you have put in all these molecules, the blue molecules here. Yeah, so you have initialized the positions. Now you also have to initialize the velocities. You can do this in multiple ways. You can either initialize the velocities in something called as the Maxwell-Boltzmann distribution. So the idea behind here is that you sample velocities from the Maxwell-Boltzmann distribution and you assign them to the, all right, that's the MB distribution. So you can sample velocities from the Maxwell-Boltzmann distribution and you can assign them to the molecules. But I will visit this in a bit more detail when we get into the script, when we discuss how to run the example to determine the densities, because there I will be able to point out several nuances that come along with initialization of MD simulations. All right, so firstly, the important thing is the calculation of forces. So once you have initialized the velocities, the positions of the molecules, you now want to calculate the forces because, as I said, in molecular simulations, you perform a Newton's equation of motion. You basically solve the Newton's equation of motion for each of the molecules within the box, and you then want to integrate the equations of motion. Yeah. So for the calculation of forces, the most important thing to know is that the force is derived as the negative of the gradient of the potential energy. So this is also very similar to what you've learned in high school, that the force is a negative derivative of the potential energy. Now, when I say Fji, it means what is the force exerted by the jth molecule on the ith molecule. And this is dependent on the potential energy of interaction between molecules I and j. Now, it's not a surprise that you can do, now j is just one single notation or an index, but now you can do this for all the j's in the system, excluding I itself. So j cannot be equal to I. So you can do all of this for all the molecules in the system, and that will be your total force Fi, or on the system or on the molecule Fi, on the molecule I, sorry. So once you know the total force on molecule I, then you can say that is equal to the mass of the particle times the acceleration. And that's more or less how the forces are then calculated for each molecule. Now, for the calculation of the forces between the molecules, the force is, like I said, a negative gradient of the total potential energy. And the total potential energy can come from many different kinds of potentials. So one commonly used potential is the Lennard-Jones potential. The other important source of intermolecular potential is the electrostatic potential, and then there are something called as angle potentials. Now, all of these are based on real physics. So you derive these potentials from basic physical ideas at the atomistic scale, or even at the quantum mechanical scale. Um, Now, I will not get into the details of how the electrostatics intermolecular forces are calculated and how the angle potentials are calculated. This will probably come at a later point in time. For the sake of simplicity and for the sake of telling you how uh, potentials are considered, I will just take up one single case of this, which is the Lennard-Jones potential, which is quite commonly used in molecular simulations to capture the properties of wide varieties of materials. So for now, it's just the Lennard-Jones potential. So the Lennard-Jones potential originates from the idea that you have dipoles associated with each molecules. It can be sometimes permanent, or sometimes it need not be permanent. And the main contribution of these dipoles is that they help molecules to become cohesive. That's why you have the negative sign. And this was introduced by van der Waals. And the idea here is that these dipole interactions help two molecules to attract each other. And this is given by this standard 1 over r to the sixth power law. Now, if you plot this minus a as, or the u due to this dipole interactions as minus 1 over r to the sixth, this is how it looks. Now, the potential energy is negative because of the negative sign, but you can see how it curves towards zero for larger distances. Yeah. Now, what is important to note is that if r tends to 0, u tends to minus infinity, which means that the closer you bring the atoms, the more closer they want to get to each other. But can this always be true? No, because if the molecules come very close together, then what happens at the quantum level is that the electrons will start to repel each other, which ultimately will start to repel the molecules apart, right? And this repulsion is, this repulsion is given by this standard power law, which is 1 over r to the 12. Now, you really need quantum mechanics to determine the exact nature of this power law, but then it's convenient to use this in molecular simulations and to use this for simulating that two molecules cannot come very close to each other. It's important to also note that people have used various other power laws like r to the 14 and so on. And for a description of this, once again, I refer you to Frenkel and Schmidt. So this was mainly due to Pauli, who suggested that two electrons cannot be in the same place at a given time, and there is an exclusion there's an exclusion coming because of this, which ultimately leads to a repulsive force. Now, if you plot this, you see that it's exactly opposite to what the attractive forces did. In this repulsive force, you see that as you go towards, as you go towards the, as you decrease the distance between molecules, the interaction goes towards infinity. So it means that you have infinite energy to associated with two molecules coming very close to each other. And you know that in nature, the tendency is to always go towards lower energy. Now, if you combine what van der Waals and Pauli's principles put together can give you, then you end up with the standard Lennard-Jones formulation, which looks like this. So the Lennard-Jones formulation has this R to the 12 that we saw due to Pauli's repulsion, and also the attraction caused by the R to the 6. So this is one of the most commonly used potentials in molecular simulations. It's simple and idealized, and it combines repulsions and attractions, and it's used widely for many different molecules. Now, there are two key parameters in the Lennard-Jones force, in the Lennard-Jones interaction potential. One is the sigma, which is the Lennard-Jones diameter, which typically you can think of as the diameter of a given molecule. And then you have the energy parameter, which kind of tells you the energy between the characteristic energy between the characteristic energy of interaction between the two molecules. Now, just to put this together and to show you the different regimes all in one plot. So this is how it looks. Now, the y-axis is once again the U Lennard-Jones. So please ignore the V here. It's the same as the ULJ that you see here. So this is exactly the same. Now, sigma tells you, so if you plug in, if you want to find out sigma, it's basically the point where the potential energy goes to 0, right? So when R is equal to sigma, so on the x-axis you have R, when R is equal to sigma, then you have this 0 potential energy. And your sigma, your epsilon is the well depth. So it gives you the depth of the potential energy, right? And as you see, if you come close enough, it obeys what Pauli suggested, that, or what Pauli showed, that molecules will not interact with each other, or they want to repel each other. But when you go far away, they want to attract each other, as shown by this dipole-dipole attraction. Okay, so now that we have an idea of what are the different kinds of forces, we now look at some of the most important aspects of molecular simulations, something that is called as the periodic boundary conditions. Now, as I told you, in this particular box, you see that the molecules are only interacting with the molecules within this box. So for example, if I pick this molecule here, he interacts with all the molecules within this box. But now what happens in this particular case is that if the box is very small, then you have a lot of surface effects, which means that there are more molecules on the surface, and as a result of which your surface molecules become more, and it becomes an incomplete set of interactions that the molecule has to interact with. So in order to or to make sure that the molecules actually interact with an infinite number of molecules, because you're simulating a very small part of an infinity number of molecules, you have to replicate somehow the system on a bigger level. And to do this, you end up with something called as a periodic boundary condition. This is a very nice trick in which you can replicate the box or make copies of the box in all directions to form an infinite system. Now, the advantage of doing this is then that you don't have any more of these surface effects, because you now have molecule 1, which can then interact with molecule 1 in this box, this box, this box, this box, and so on up till infinity. And you then don't restrict its interactions to just the molecules within this box. Now, the way the periodic box is constructed is that if the molecule moves to this particular box here, then it enters back into this box again. right? So similarly, if molecule 2 is moving in this direction, then according to the periodic boundary conditions, in all of the boxes, your molecule 2 would also take the same course of the direction, or molecule 2 would move in the exact same way as it did in the first box. Yeah. Okay, so this is basically the periodic boundary condition. Now, as you can see, if it enters or if it leaves one side of the box, then it should enter from the other side of the box. So ultimately, there's no loss of mass of these molecules from the box, and they always are within the box. Now, how they enter are defined by these periodic boundary conditions. Now, the obvious problem with obvious implication of using periodic boundary condition is that you have to think now that this molecule 1 is not just interacting with this molecule here, or not just interacting with these molecules here, because you've made infinite copies of these boxes. Now molecule 1 has to interact with all the molecules in all the boxes, which means that you have to basically take into account infinite number of interactions. You can of course do this and your simulations get more accurate, but at the same time, it's also very computationally expensive. So you do not want to do this for all the molecules and all the time at all the times, because then you only end up calculating the forces and you will never do anything more than just calculation of forces. So now for this reason, what one has to do is, or what one typically does, is choose an interaction cutoff. So this is another very important concept in molecular simulations, that you choose a cutoff radius. So what the meaning of this is that you choose the cutoff radius called RC, and you calculate forces only between the molecules within this cutoff radius. And if the molecules are beyond this cutoff radius, then you say that I do not care, and I ignore the interactions with the other molecules. Now, if this is the case, if you have an interaction radius, now the important thing is that you also have to take into account the distances between the different molecules. And to calculate the distance between the different molecules, you need to consider something called as the minimum image convention. In the minimum image convention, what is important is that, let's say, okay, to show this more clearly, let me see if I can do this. Okay, perhaps not. Let me try this. Now, this is molecule 4, and this is molecule 1, and this is molecule 4, but in a different periodic box. Now, if you have to calculate the force between molecule 1 and molecule 4, you end up with two different distances, right? Now, one of these falls within RC, or one of this falls within the cutoff and the other doesn't fall within the cutoff. So now which of the two molecules will you choose? And the way to do this is to calculate something called as the minimum image distance between molecule 1 and molecule 4. Between molecule 1 and molecule 4. So according to the minimum image convention, what you do is you choose the distance that is minimal between any two sets of molecules in all the different periodic boxes put together. So once you know the minimum distance between the two, you choose or you pick only that distance for calculating the interaction between the molecules. And then you only need to account for one single nearest image of the molecules in question. So here it's 1 and 4. But now, if you want to do this, as I said, the truncation is a very nice, or choosing a cutoff, RC, is a very nice way of restricting your number of interactions and choosing a particular set of interactions. But what also ends up happening with this is that your number of truncation leads to neglect of these interactions here. So we say that we're only going to calculate interactions up till this particular distance. Now, for distances greater than this particular RC, which is say a 2.5 sigma, which we call, in which sigma is the distance here. So now if you neglect all these interactions beyond 2.5 sigma, then what happens is that these will have an effect on your molecular simulations, will have an effect on your results. So you need a way to somehow account for all of these interactions beyond the cutoff. And for this, we introduce something called as the long-range correlations or the long-range corrections. Sorry, not correlations, but corrections for both the energy and pressure. The idea basically here is that you integrate over all the distances from the cutoff to the infinity, and you calculate the energy of interaction between the molecule that you've chosen and all the molecules beyond the cutoff. And then finally, you pick a sphere of radius 4 pi r square, or you pick a sphere of molecule 4 pi r square dr, and you choose all the molecules within that. And the way you do that is you multiply it with the number density rho. And then you also have a half to account for the double counting. So I'm not getting into the details because this is quite well given in Frankel and Schmidt. The idea to point out here is that if you choose a particular cutoff, you definitely need to choose or you need to correct for these long range effects, because you're effectively neglecting all the interactions beyond this cutoff distance. So once you do this, you can calculate what this tail contribution is to the energy. And similarly, you will also have a tail contribution to the pressure, because the pressure calculation also requires interaction between molecules that are separated by a distance r. So you also have a contribution that you need to consider from the cutoff to the infinity. Yeah. So once you do this, you end up with this tail correction for the pressure. And these are extremely important to use, especially in NPT simulations, where you have to calculate the appropriate pressure, and you want the system to finally equilibrate to the right pressure. And this is something that we will use in our simulations, or the example that I will show later on. Finally, you also want to, when you're looking at Lennard-Jones potentials, you want to truncate. So the important thing in most of these things is once you truncate this potential at this particular point, what happens is that you have a discontinuity. So you have a particular potential energy at a given distance RC, and then the potential basically becomes zero, right? So there is a discontinuity that is associated with a particular cutoff. So what is commonly done in molecular simulations, which is a good practice, is to shift the potential to zero once you have truncated it. So once you truncate it at this point, you then shift this entire potential by this amount, which is called ULJ shift. And by shifting this, oops, I'm sorry. Once you shift it, you get your system back to the, you make sure that there are no discontinuities in the system, and this makes it a bit more susceptible to errors. Okay, so As a final note, what you should know is that now that I've told you that Lennard-Jones potentials have been used for a wide variety of molecules, you can see that the Lennard-Jones, there are parameters available for Lennard-Jones in many standard texts. So you can look at Lennard-Jones potentials for argon. So you know that there's a sigma and an epsilon associated with it. There's something for neon, krypton, xenon, methane, and so on. So if you know the sigma and you know the epsilon, you basically know the Lennard-Jones potential and how the molecules interact between each other. So these values have been tabulated for many different molecules and for many different materials. And I will go through this in one of our upcoming examples. Finally, once you know all the forces on the different molecules, you now have to calculate the positions and the velocities. Or you have to update the positions and the velocities. Like I said, for this, you have to integrate the equations of motion, which is from the Newton's equation of motion. And one of the common algorithms for doing this is called the Verlet algorithm. And in the Verlet algorithm, what is important to note is that the position, that is r of t plus delta t, or the position at a time t plus delta t, is only dependent on the position at that particular time t, and then the time at t minus delta t, and the forces, of course, on the molecule. Kindly note that there is no dependence on the velocities. So this is completely dependent on the positions and has no reference to the velocities. So this is only position dependent, and there is no velocities. Now, you can calculate the velocities from the positions, and this is how you do it. So this is the formula for calculating the velocities of particles, and this can be calculated using the positions that you have calculated at r of t plus delta t, and using the positions at r of t minus delta t. Note that the order of accuracy is around delta t to the power 4, and here the order of accuracy is delta t square. Now, the main advantage of using the Verlet algorithm is that it conserves energy and it is time reversible, which is very important considering that simulations run for very, very long time. And if you want reliable results, you want your simulations to conserve energy, which means that there should be no addition of energy into your system, or there should be no removal of energy from the system. And it should be time reversible. When I say time reversible, if you simulate it backwards, you should end up with the exact same position at which you started. And these are very important when you're performing molecular simulations. And that's one of the main reasons why Verlet algorithm is commonly used for integrating equations of motion. Now, all of these are available in Frankel and Schmidt, and there are various versions of the Verlet algorithm, like the leapfrog integrator as well, which all work on the same principle. So finally, after you've calculated the positions and velocities and all that, you then calculate physical properties that you're interested in. Now, I will not explain which physical properties you can calculate here. We will do this in the example that I plan to show you at a later point.